Um, Also, how about the pointer? Looks good? Okay. So thanks, Seth, for inviting me to this journal club. Today, I'm going to talk about Anderson localization and beyond, where beyond means some brief thing about many-body localization and the research I did at Caltech. So feel free to interrupt me if you have any questions. The outline of this talk I will do bring in the story of Anderson localization from the Einstein relation. Then hopefully it will be a pedagogical introduction to Anderson localization. And then we'll turn into some maybe technical parts, which is about the research. So the main resource is from this book, Modern Condensed Matter Physics, that is written by Griffin and Young. I actually copied many plots and equations from there to the slides. And here's the paper that I made from that undergraduate project. The title is Anderson Localization on the Bethe Lattice using cages and the Wagner flow. Some from the title, maybe you can imagine it will be a bit technical in the second part. This project is made with Samuel Savitz and Professor Durafield. So let's start the story. We know there's an Einstein relation, which is a relation between the conductivity and the diffusion constant in condensed matter. Written in a formula, it says sigma equals E squared times dN over d mu times d, where sigma is the conductivity, d is the diffusion constant, and dN over d mu. In a single particle system, it says the density of state per volume at the Fermi level, but for a many-body system, there might not be a clear definition of single particle orbital, so it's replaced by isothermal compressibility. Maybe some of you haven't seen this before. At least for me, I didn't know it's called the Einstein relation before I prepared this talk. So let me show you a brief proof. Considering a condensed matter system in equilibrium, so in equilibrium, it means that the particle flows driven by the electron field should be compensated by the particle flow driven by the density difference. So here, this is the electron current, and this is the density current from the diffusion, and they should add up to 0. We know that this density difference coming from the potential difference and multiplied by this density of states. So adding all these up together, we finally get this Einstein relation, which says the conductivity is proportional to the product of density of states times the diffusion constant. So what can we see from this relation is for an insulator where sigma equals 0, is either dN over d mu, the density of states equals 0, or d equals 0, the diffusion equals to 0. Or certainly there is a third possibility that E equals to 0 means nothing in the system carries charge, but in most condensed matter systems we are interested in, there's always electrons in it, so we ignore that third possibility. So let's see what it means for the first possibility, dN over d mu equals 0. So for a single particle system or for band systems, it means at the Fermi level, there is no density of state. This comes with the band insulators. Here is an example of a diamond and the band structure for the diamond. You see at Fermi level, the 0, here, there's no band crossing. So the density of state there is 0. And a second example is Mott insulators, where although there are mobile electrons in it, but however, for some reason, like interactions or on-site potentials, the average number of particles doesn't change with chemical potential. So here is the phase diagram for a Bose-Hubbard model. In this blob, the density of state is always 1 equals 1. It doesn't change with the chemical potential, which is on the y-axis. So we also have dn over d mu equals 0 in this case. Actually, I pretty like this egg image presenting the Bose-Hubbard model. And an insulator phase, the eggs are sitting at each side locally. And in the superfluid phase, the eggs are beaten and they can flow like liquid to other side. Well, in the second possibility that the diffusion equals 0, in this case, it's called Anderson insulators, where in the system, there is absence of diffusion due to quantum interference with scattering of the disorder. This phenomenon is first brought up by Philip Anderson in 1958 from his famous paper, Absence of Diffusion in Certain Random Lattice. So here is a plot for possible Anderson insulators. With some disorder, there is some part in the band which have localized wave function, where I'm showing here. The wave function for the particles are no longer extended in the whole system, but exponentially localized at some sites. And notice that the states that are close in energy have the wave function position that might be far spatially, and the site that is close in spatially have energies far apart in the spectrum. So the diffusion between those states are exponentially small. So there's no diffusion in the system. It brings it to an insulator. So let me go into Anderson localization. Here is a classical picture of a solid which have atoms in it, and an electron might bump into an atom and scatter. Well, actually, this picture is not quite right because we know electrons are forming the Bloch waves and act quantum mechanically. But in Feynman's path integral, we can still view it as this like classical picture for the classical paths. Well, in the quantum picture, the electrons are behaving like these Bloch waves. If it's a perfect lattice, then as you've seen, the Bloch waves just traveling without any restrictions. But if we have a disorder noted by the green dots in the center, we might have some scatterings of the wave functions of this disordered sites like this. So you can see the wave travels and then there's a green wave traveling back. That's the scattering. So there's some basic observations in a disordered system that, by the way, everything here is stated at 0 temperature. So for a non-interacting system, which means we have a single particle picture for it, in 1D and 2D, any weak disorder can localize all the states. Like it's not like here we have a mobility edge where below that the states are localized and in the range some states are extended. No, in 1D and 2D, all states are localized. but there's still some difference in between 1D and 2D. In 1D, it's even more localized. It's called strong localization. But in 2D, the localization length scale can be exponentially large. So sometimes the localization length can exceed the size of your system or exceeds the coherent length bring by finite
Could I ask a
temperature
very
system.
basic question?
Sure.
How are you quantifying the level of disorder? Is this just like, are you
Um,
defining disorder by a single local impurity and then scaling its uh,
it and it can be quantified by the density of impurities in the system. And it also has some factor with how are the impurities different from the regular atoms in the lattice. Or if we bring it to the tight binding model, we can say there are on-site randomness at each on-site random potentials on each site, and they are not correlated, or there might be some correlation between them. And the variance of the on-site random potential can be a quantization of the disorder.
So, sorry, just to be clear, which are those all the same thing or different ones? Because I understand having like certain density of impurities, but that seems like a very different way of quantifying disorder than taking a tight binding model and then on every single site adding some amount of random on-site potential. I'm just
Um, um, on every site, there's an on-site potential. It's more like a toy model that
okay.
to describe this feature of their actual impurities in the solids.
So the measure of the strength of your disorder is a density of these impurities, and there's some other quantifier for how different they are from the base lattice. Is that
Yes, because you can imagine if the potential bring by the impurities is very large, or the range of the impurities is very large, then the effect of scattering is larger. If the impurity is not much different from the regular atoms, then it might only contribute to
yeah?
smaller scatterings. Yeah.
Just wanted to get a quantitative measure. Cool.
Okay. So 2D we have weak localization, which means we might not observe the localization effect because uh, the localization length is large. But in 3D or higher dimension, there exists a critical disorder. Above the disorder, the system is localized, and below that disorder, we can see something similar to this. Are still some extended states, and there is a metal insulator transition. For example, if we have our Fermi level here in this localized range, then this uh, thing is an insulator. But if we decrease our disorder, the extended states gets broadened, and when this mobility edge, which means the edge between the localized states and the extended states pass this Fermi level, then at the Fermi level, the states are extended. They have finite diffusion constants again. Then we enter metal phase. So this can be a possibility resource for the metal insulator phase transition. So how can we understand this with perturbation theory? So we can think of a single impurity bring up some potential, and the Bloch waves is scattered from the single impurity. This will study in quantum mechanics class. And for multiple scatterings, for a density of impurities, we can use the path integral methods. However, from block waves actually to a localized wave function that exponentially decays with distance, this change is non-predictive. So it means that in our treatment, there's some step that brings divergence. So let's see where the divergence comes from. So in a real space picture, like these are the impurities. We have our path integral description, like the amplitude of an electron scattering of these impurities are like constructively interference with the amplitude that it goes backwards, scattering off these impurities in this way. So this quantum interference tells us in a quantum system, the probability of an electron returned to its original place is higher than it is in the classical case. This higher return probability will lower the diffusion constant. That's one quantum effect, quantum correction to the diffusion we can see in the real space picture. So also we can see from the momentum picture, which was time reversal symmetry. The backscattering, which means a particle with momentum k scattered into a particle with momentum minus k. This process is also enhanced because of the constructive quantum interference. For example, if it started with k and then scattered into k1 and then k2 and then to minus k, we can imagine a time reversal process that it scattered to minus k2 to minus k1, then to minus k. Two processes happens to have the same amplitude in this like path integral formulation.
What would happen, maybe this is obvious, but like if I introduce a magnetic field, I'll break time reversal and then I'll make these in the real space picture. The phases will be different.
Yeah.
And so could I then go from a localized state to an extended state? Like
yeah.
my states are localized, I introduce a magnetic field, I then go to an extended state.
Yeah, I think magnetic field will break the localization, at least for very weak disorder. A magnetic field will break the localization. Actually, in the integer quantum Hall effect, we see that the crucial reason we have a very stable or very flat platform, integer platform, is that we have some
disorder,
value of disorder in the system. Yeah. So this enhanced backscattering, actually, we can see it in daily life with like this optical phenomenon called glory. So if you've ever like taken a flight or climbed up to the top of a mountain where in far distance there's a foggy cloud and there's a direct sunlight behind you, you can see in small angles there are a light ring around you. So this comes from the backscattering, the momentum k to minus k. This process is enhanced from this constructed quantum interference. Another effect from this enhanced backscattering is that if we input a pulse to the system, it will bring a negative current echo because the backscattering is an extra piece to the classical process. It's a quantum correction. So we have a negative current echo. So using the linear response, we can formulate the conductance, the correction to the conductance from this correction of this negative current echo using this. And we want to see how the DC conductivity change. So we take omega equals to 0, and then it means the area of this negative current echo, the time integral of it, brings up the correction to the DC conductivity. The formula for this current echo, it decays not exponentially, it decays with like the formula T to the minus D over 2. That power D over 2 coming from the return probability in dimensional D. So we can see here at D smaller or equal to 2, this area, the time integral of this echo current diverges. But for D greater or equal to 3, we have a finite correction to the conductivity. It means in 1D or 2D, our perturbation actually fails. We will have some non-perturbative effect, non-perturbative correction to the conductivity. But in 3D, we have a finite correction.
Is there some way to see why it scales as T to the D minus D over 2?
An idea is when you will have an echo when that enhanced backscattering or this quantum correction to loops appear. So at time t, then this correction appears with a probability the same as if you start a particle and it just random walks and walks back to the original point, is proportional to that return probability. So the larger it returns, the probability it returns, then the larger quantum correction to it, then the larger this negative current echo is. I'm not sure if it is a good explanation.
That's fine, thanks.
Okay. Okay, so now we see one explanation of why in 1D and 2D we have that localization. All states are localized for any value of disorder, but in 3D we have that phase transition. So in low dimensions in 2D, the weak localization means the localization length actually is exponentially large. It has a form like e to the some number times kf times L, where L is the mean free path between two scatterings and kf is the Fermi momentum. And KFL, if we have weak disorder, and in the semi-classical picture, KFL is usually much greater than 1 because KFL is the ratio of the mean free path to the size of the wave packet of the electron. So we can see E to this KFL can be a huge number. So even the mean free path is a microscopic value. This localization length psi can be a macroscopic value. So it might easily exceed the system size or exceeds the coherent length. So in 2D, in some 2D systems, we might ignore the effect from like weak disorder just because there's weak localization effect. However, in 1D, we have a strong localization. It means that the localization length psi is roughly the scale of the mean free path. We can easily see that because in 1D, every scattering is backscattering. So in 1D, if we are not moving forward, we are moving backwards. So an electron immediately feels this quantum correction of backscattering after the mean free path. So that's why in 1D we have very strong localization. In 3 dimension, the perturbation converges for weak enough disorder. Therefore, the metallic states in 3 dimension is stable against weak disorder. So we have a metal insulator phase transition. Like for large enough disorder, certainly everything localized. But for weak enough disorder, we have extended states and metallic states, so there has to be a phase transition somewhere. So this is the plot again. We have our Fermi level here, and it sits in a localized range, so it's an Anderson insulator. But above some gap, we have the extended states. This gap is usually called the mobility gap. In this type of Anderson insulator, it sometimes behaves similarly as a semiconductor, which also has a activation gap. So if we have some finite temperature and the electrons can excite to this extended states, then it can diffuse and carry current. So we have conductivity from that part. But the electrons in this localized range, they are non-diffusive, so they have contribute 0 to the conductivity. So when we have a phase transition, we can ask questions about what happens at the critical point. So there is something interesting there in the Anderson transition, where the wave functions show a multifractal structure. So this is a picture of what a multifractal structure looks like. This is a simulation of Anderson model at the critical transition point. The colors are showing the intensities of the wave function on the sides. This is a spatial plot of the wave functions. We characterize the phases using this so-called inverse participation ratio. So the definition is the 2q momentum to the wave function. It has this property. So if in the localized states, this q power momentum is independent of the system side. You can see the wave function is localized in some finite range. So it doesn't matter how large the entire system is. But if we have extended states, then we have some normalization factors in this wave function. So this inverse participation ratio will depend on the system size in the scaling law. And at the phase transition point, we have this multifractal structure, which says the IPR is the scaling law have a coefficient that depends on the value of Q. So for DQ, this is the fractal structure, the fractal dimension D. And it depends on Q. It says viewing different Q power momentum of the wave function at the critical point, we actually have different fractal dimension of this wave function. So this is the multifractal structure. And since we've talked about the scaling theory, I will show you another kind of statement why we have localization in 1D and 2D and a phase transition in 3D. So suppose we have a dimensionless conductivity GL. the L is the system size. And suppose we have this relation in the scaling theory. We bring L to some larger cubic system into a larger cubic system where the side length is increased. And we see how this dimensionless conductivity scale with this increasing of system size. Suppose we have beta G, the scaling power is beta G. In a good metal limit, where G is much greater than 1, we have this Ohm's law. The dimensionless conductivity scales as D minus 2, the system size over D minus 2, to the D minus 2 power, right? In 2D, the dimensionless conductivity is independent because we bring this resistance parallel and in sequence, and they cancel with each other. So 2 minus 2 is 0, for example. And in the localization limit, when G is much smaller than 1, we have this dimensionless conductivity scale as e to the minus L, because the wave function in the localization limit has this length decaying length scale of psi, and the overlap between two wave functions is like goes to e to the minus L over psi if these two sides are like roughly that has distance L between. So we can calculate beta G in this limit using this d log G over d log L. And after the calculation, you find that beta G goes to log G. So we can smoothly connecting these two limits. Like when G much greater than 1, we have D minus 2. When G much smaller than 1, we have log G. We plot beta G versus log G. We see that in 3 dimensions, this D minus 2 is 1, so it approaches 1. In 2 dimensions, it approaches 0. In 1 dimension, it approaches to minus 1. The crucial part is that we only have a crossing to the beta equals 0 in the 3-dimensional case. So when we increase the system size, we have this log L increasing. So if beta G is positive, we have G flowing to a larger value. So if it's positive, when we increase system size, it flows toward this good metal limit. And if we start with a negative beta, then it flows to G equals 0 to this localization limit. This is the case in 3D, but in 2D and 1D, we always flows to this localization limit, which means we always have localization no matter how small, how weak disorder there. And it's weak localization in 2D because we see this lines approaches 0 very closely when we have a large G value. So actually the flowing to this localization limit is very slowly. So we have that weak localization in 2-dimensional system. So finally, let's talk about the Anderson model, which just simplify everything into a toy lattice model, where we have hopping between different sides and an on-site random potential on each side. And there's no correlation between different sides. Typically, we set this random on-site potential is distributed uniformly in this range, minus W over 2 and W over 2. And the value of W is the definition of disorder in Anderson model. So what Anderson showed in his 1958 paper is that if we treated the hopping as the perturbation and the non-perturbed case is where every site has its own site potential and the waves are localized at each site, the bases are the sites, then this perturbation series will diverge in 1D and 2D, mean means, sorry, maybe I made a mistake there. I think is converged in 1D and 2D. So we always have localized wave function in 1D and 2D. And in 3D, there is a critical value of disorder where below that it diverges. Actually, it should be converges. And above that, below that, it diverges. So our on-site wave function approximation is no longer valid, and we go into the extended state regime. And above this critical value, it converges. So this localized wave function approximation is valid. We are still in the perturbation regime of a localized wave function. Yeah. So I need to choose the words here.
I had one question about this picture you're showing. Maybe it's a silly question where there's this density of states and your energy, and your extended states are right in the bulk of your density of states. Is that always the case?
I think it depends on the details of like the lattice geometries and the details of the system, but there's always a mobility edge. Like the extended states and the localized states are always separated. That's the feature. I think there's some result saying that if we have this density of states range very far in energy, then any small disorder can create some localized states at the edge, at the boundary of the band. But I'm not sure, like I'm not 100% sure about that statement. But the localization transition means we no longer have this extended range, like the mobility edge collapse at E equals to 0, and all these states are localized.
Interesting. I guess at the edges of your bands, your Fermi surface is very small. Like if I'm dragging up mu, and so the smallness of the Fermi surface, does that enhance backscattering in any way and make localization easier? Like, is that why it happens at the edges?
Yeah. And also maybe the energy there, because they are far from this.
There, got it.
Average energy. Yeah. Okay. So with that, things might depend on actually the actual lattice symmetry. And we talked about what happens in the 1D lattice, 2D lattice, and 3D lattice. Here I want to say something about a different lattice, which is called the Bethe lattice. It is a loopless graph. So each lattice site is connected with 3 other lattice sites, and then it extends to infinity and is loopless. So this is the Bethe lattice. It's a tree, which means it's localist, and effectively is infinite dimensional. We can see that from how the number of size grows with the distance. So dimension is defined in that way. So the number of size grows exponentially with distance. Actually, it's 2 to the distance. So this exponential behavior tells us it's effectively an infinite dimensional system. And there is also self-similarity on this lattice. Like each lattice side is self-similar to any other, and this branch is similar to this branch. With this self-similarity, the Anderson model on Bethe lattice can analytically be solved. In 1973, it's solved by Abel Chakra and said there's an Anderson transition at WC roughly equals 18T. We will come back to that, why we said is solved in quote, because there is something missing in the solution as Abel Chakra has given. So what we have discussed previously are all in 0 temperature. So let's see what happens in finite temperature. In finite temperature, the system interacts with a thermal bath in the environment. That thermal bath will dephase the charge carriers. And after some coherent time, the electrons are dephased completely. And the length it travels, we call it the coherent length scale. So beyond this length scale, there is no quantum effect. Everything is completely dephased. And we go back to the semi-classical case. Since beyond this scale, there's no quantum correction, so there is no enhanced backscattering or anything we talked earlier. So there is no localization effect beyond the coherent landscape. And so beyond the scale, we have our diffusion back, we have our thermalization back, and localization only appears inside this so-called coherent blocks, which is the coherent time, a length scale times coherent length scale. So a question is, with interactions, can an isolated system act as its own thermal bath? So adding interaction to this non-interacting systems, can a part of this system thermalize the rest of parts of this system and make the localization behavior disappear? So that is the question of many-body localization. So the motivation is that with interactions, the single particle picture is no longer valid, and instead we have wave functions living in a much larger Hilbert space. And we ask the question, can this order generate a localization in this Hilbert space? If the answer is yes, then an isolated system doesn't diffuse in this Hilbert space, as we've seen, like in the case of a localized wave function, then the electron just move inside this localization length. So if in the Hilbert space it localized, then the system stays only in a finite range and it doesn't diffuse to other possible states. So those systems never thermalize and it always remembering its initial states. If such system exists, it will be good for quantum computing because we don't want the thermalizing effect happen too often in the quantum computing. We want things to remembering its initial state. So we need another definition of localization in this many-body picture. So since I'm going a bit slowly, I will keep fast in the rest of the slides. So here, the definition of localization changes into we have some local observables commuting with the Hamiltonian. So we have the local integrals of motion or local conservation laws that prevents the system to diffuse or to change these local values into some other local values because we have these local conservation laws. In formula, it says with some local unitaries, we can change the Hamiltonian into the product of those Q bits or those local bits called tau, and all the taus are in the Z bases. So it's either 1 or -1. So with these quantum numbers, we can label the states of the system. So they just localize in the Hilbert space. So the example is a spin on a lattice. The Anderson model is equivalent to this spin model where spins can hop around on the sides, and we can add interaction to make it a many-body system, like the nearby spins are interacting with some coefficient. This is a many-body system and hard to solve. And in the extreme case of no hopping, like setting Tij to 0, this Hamiltonian is actually easy to solve. We just have our eigenstates of have like either +1 or -1 on these different sides. Those +1s or -1s are the local conservation laws. And once we have a spin to be +1 on the side, it never changes into -1. So this is the localization in phase space, or the no diffusion, or the remembering effect of the initial states. So that's the idea. And what does it mean we have like many-body localization? So why do a quantum system actually thermalize in the first place? Because in quantum mechanics, everything is unitary. If we start with a pure state, then we will end with a pure state. How can we have a thermal mixed state? So the eigenstate thermalization hypothesis states that if we separate our system into parts, then after the evolution given by the quantum mechanics, the parts will fully mix with each other, and for each part, the density matrix looks like a thermal density matrix in a long time average. But that depends on we have non-local conservation law or even no integrals of motion. But if we have local integrals of motion or local conservation law, then this mixture of different parts in the quantum state, that doesn't happen. So that violates the eigenstate thermalization hypothesis. So whether this many-body localization exists is not sure since 2006. Basco and Alainer and Altschuler shows that in some system, it exists and is robust to local perturbations. So we finally found some system that violates the eigenstate thermalization hypothesis. And furthermore, in 2016, Pino shows that in Josephson junctions, there is even states that has finite resistance and an entropy smaller than thermodynamic value. They call the state bad metal, which means for finite resistance is that the particle diffuses. And entropy smaller than thermodynamic value means they don't fully thermalize. So those states are interesting because they diffuse. they are extended states, but they don't thermalize. They have this non-ergodic behavior. They don't fully explore the phase space of this entire Hamilton Hilbert space. But many-body system has problems like in numerical simulation because the Hilbert space is too large. So we need to find an effective way to simulate that and just see if we can have some numerical evidence of this non-ergodic extended states. So here brings to my second part. Unfortunately, I think it's almost the time here. So I will briefly introduce the idea of how we turn a many-body localization problem into an Anderson localization problem on Bethe lattice. So there are several steps. First, we observe that the many-body localization is actually a single particle localization on this huge dimensional Fock space. And there's no approximation there. So we can label each state of the many-body state as a site on the Fock space. And the transition between the states are just the particle hopping on this Fock space. But in this Fock space, if we have any disorder originally in this many-body picture, the spatial disorder will bring a correlation in this Fock space disorder. We use our first approximation that assuming this correlation can be ignorable if we go to large enough system. And then second approximation is this infinite dimensional hypercubic Fock space. If we start from any site, then it's very not possible that it will finally come back to the original site because on each hopping, there's infinite number of choices it can hop into, so it will not choose to going back. So we can approximate the hypercubic lattice into a lattice without groups. So this is Bethe lattice, but it has infinite coordination number, which means each site has infinite number of neighbors. And our third approximation, we assume that this infinite number can be reduced to 3. So we had our previous plot of Bethe lattice, each site has 3 neighbors. Hopefully, these approximations will keep the key features of many-body localization to this Anderson localization on Bethe lattice. And then so people actually don't agree with each other about whether such non-ergodic extended phase still exists in this simplified model of Anderson localization in Bethe lattice. Some people think, oh, this ergodicity phase transition exists. Some people think all the extended states in this model are ergodic. And there are some other papers showing that all the extended states in this model are non-ergodic. This discrepancies appears because people use different finite models to describe actually
By the way, just ergodic here means visiting every site. So like the wave function has some density on every site, right?
Yes. Yes.
Okay.
Yeah. So the discrepancy is coming from how people realize the infinite lattice with some finite geometries that can be simulated on the computer, or the other indicators of what it means by ergodicity, what it means by extended or localization. We've previously seen the inverse participate ratio, the IPR. There are other indicators such as the level spacing statistics or some other stuff. So people use different methods and got different results. So I think there's still no final conclusion of whether this still happens in this Anderson localization on Bethe lattice. I'll skip with the details in our research because it's almost the time. So the conclusion is, so this is a beautiful plot. So with our method, we find some hints that this ergodicity transition appeared, but this is not a final words to this discrepancies because we also use some very non-trivial approximations or indicators to further interpret the problem of Anderson localization of Bethe lattice. So how largely this represent the original problem is not certain. So we can draw three phases. One is localized phase, one is non-ergodic extended phase, and another is the ergodic phase in a parameter space. And the color bar here is showing the disorders. So we can see in high disorder, our indicators showing that the system in a localized phase, and decreasing the disorder at the value of around 16, we get the localization extended phase transition. And further decreasing the disorder, we enter this ergodic non-ergodic transition and in this ergodic extended state. So our conclusion is that, oh, this non-ergodic extended intermediate phase does exist. And what it means, like in the sketch, is that in a localized state, the system won't spread much and the wave function decrease exponentially with distance. And in a non-ergodic case, it's extended. So it means that there are certain branches that the wave function has significant values on, but it doesn't explore all these branches. And an ergodic extended phase, it means that on every side, there's a significant value of wave functions on it. So that's the picture. And here is another plot showing how this branching ratio, the branching ratio smaller than 1 means the states never extend to farther distance. Between 1 and 2 means it explores some certain range, but not smaller than 2 means not all these branches. And equals to 2 means it explore all these branches. So it equals to 2 when the disorder is below some critical value we call WE. E means ergodic, non-ergodic phase transition. And it crossing 1, which is the extended localized transition, which is WC, we mentioned before. And here, these are the three regimes, the three phases. Well, what it means of we have 3 lines or 3 values of WCs, I will ignore those details here because of the time. So some future research might be, well, to understand how reliable are these approximations we made from an many-body localization system to an Anderson localization model on the Bethe lattice. And second is to understand what happens on this Anderson model on Bethe lattice. It itself is a very interesting question. Yeah, so whether this ergodic city phase transition appear or not, I don't think people have a final conclusion to that. So thank you. That's all for my talk today. question?
I guess I had, is there any literature, or maybe your research, is there any literature that hints at what an ergodic phase transition might look like? Like, I mean, I see from the picture of this like branching, but would we expect it to basically look like, let's say we're looking at a metal which has that transition, would it be exactly the bad metal phase, like this non-ergodic phase? Or is that only like an approximate picture? Like is the bad metal description, does that map exactly onto the...
I don't think there's an exact mapping between that, but on the many body side, the bad metal has a clear definition of their resistivity goes exponentially with the temperature.
Right.
And yeah, but I don't think here you can still actually talk about the conductivity through the branches, but you need to define the leads or some detailed issues there. It still has some similar argument of the exponentially large resistance or something like that. But whether there's a one-to-one mapping, like we have that metal phase and this correspond to this.
I think what I was really confused about is how you would go from this, because obviously your this infinite dimensional Fock lattice kind of description, it's not intuitive to me how that map, like what quantity you would define there that would map to resistivity in the normal metal. Like, yeah. I understand the branching, I think. But going from state to a different state in the Fock space isn't the same as like going from a real space point to a real space point. So I was just curious about that, I think.
Yeah, but I think that's a good question, like how to interpret this Bethe lattice, because we look at this here spatially, but in the many-body picture, like these are not like spatial size, these are size in the Hilbert space. Yeah, I think that's a good question. And I don't think I have a clear answer to that.
Okay. Cool. Any last questions here? All right. If not, thank you, Changmin. And next week we will hear from Felipe. He works with Debanjan at Cornell, and he'll tell us about bad metals and Fermi liquids. So I hope to see everyone next week. All right. Enjoy the snow.